Hi everyone, let's go ahead and get started, please. A couple of things to talk about before we talk about today's very, very important topic. First thing to discuss is office hours this week. So it's kind of a crazy week. Some of my TAs are going out of town. There's some stuff happening on campus. There's apparently a new chancellor and some other stuff that's going on that's just going to make campus crazy towards the end of the week. So office hours this week are turning out to be a little bit tricky. I know you've got an assignment due, so I just wanted to make you aware of the changes that are happening to office hours for this week. Emily and Ellen's office hours on Wednesday are canceled. They are not going to be here. They will be gone. But I am going to hold office hours on Wednesday before class to try and compensate for that. And then I'm also holding longer office hours on Tuesdays and Thursdays. Normally I only run office hours for an hour and a half on those days. I'm going to try and run for a little while longer on Tuesdays and Thursdays, so that if you need help on homework assignment number 2, you've got an opportunity to come in and ask questions to get help on that homework assignment. The other thing to be aware of is that with all the other events going on, they basically told everybody don't drive to campus because there's not going to be anywhere to park. So I'm taking the train, which is fine, but please be aware that I am at the mercy of the train's schedule. So I'm going to try as hard as I can to be here on time for office hours, but please just bear with me. It's a crazy week. I'm doing the best I can. I'm going to try and get there and be available for you all. Just don't be surprised if I happen to be a few minutes late for whatever reason. Any questions on office hours? Okay. The other thing I wanted to talk to you about is the homework grading. We are actually so very close. I was finishing things up before class, and unfortunately there were maybe, I don't know, 3 or 4 homework assignments that I just ran out of time. So odds are that you've got a grade. Most of you in this room have a grade on homework 1. There are a very small number of you, probably can count on one hand, who do not currently have a grade. We just ran out of time. I'm going to try and get to those tonight, so you should have that fixed by tomorrow. So if you happen to be one of those unlucky people, I'm sorry. We're actually doing very well. We're almost done. It's just going to take me a little while longer. If you have questions about your grade, if you want to talk about any points that were taken off, I'd be happy to talk to you about that via office hours. That's actually my preferred way of doing it. Although, of course, I'm happy to answer questions over Piazza or email as well if you can't attend my office hours for whatever reason. So those grades should be in your repository. You should find a file in your repository called homework1.txt that explains what points were taken off, if any, and then you should also see the homework grade on Canvas that should hopefully match the one that's in your repository if I typed the values in correctly. So take a look at that, and again, like I said, if you're missing it, then you're just one of the unlucky few that we haven't gotten to yet, but soon. We're almost done. Any questions about that stuff before we hop into today's very important topic? Any questions about homework 2, I guess I should ask while we're sort of on the topic as well. Anybody have anything they'd like to talk about in regards to homework 2, which is due, I believe, next Wednesday, correct? Doing okay so far? Is it due Monday? Sorry, due 1 week from today. My apologies. Any questions? Okay. Well, if you do have questions, like I said, I'm trying to hold a lot of office hours this week, so please come in and see me. Love to chat with you about homework 2 or homework 1 or whatever you want. It's up to you guys. Otherwise, let's go ahead and get started on today's topic. I'm glad you all came today because this is a very important topic for this class. We're going to talk about Btrees. So this is a quick little refresher. You'll remember that towards the end of class last Wednesday, I introduced the concept of a B tree. So a B plus tree is going to be a slight variation or actually a pretty significant variation on this concept of a B tree. Why are we even talking about trees in the first place? What are these trees being used for? What's the point? Why are we using these trees in our database? What purpose do they serve? Just because we like building trees? I mean, I do. I think it's pretty fun, but is that the reason why we're spending this time talking about trees? What's the whole point? Yeah. Reduce our search time to help us look values up. It's a secondary access, right? Secondary form of access into our data. So hopefully a faster one. So a B plus tree is actually a very widely used data structure when it comes to this purpose, when it comes to indexing tables in a database. So let's talk about what a B plus tree looks like. In class on Wednesday, you'll remember that we talked about B trees, which have data and then pointers, either pointers the data itself is a key value pair, where the key is the search term and the value is the page in the table where that search term lives. And then in between those key value pairs would be pointers to other nodes in the tree, right? The biggest difference between B trees and B plus trees, which is actually a very huge difference, is that I'm going to have internal nodes and leaf nodes. And the purposes of the internal nodes and the leaf nodes are different. The internal nodes are used only to point to other nodes of the tree. That's it. They do not store key value pairs. Or another way of thinking about it is they do not contain the content of my index. They are used for searching only. That's it. The leaf nodes are where the key value pairs are going to live. The leaf nodes are where the index terms are going to live and the page pointers into the table are going to live. So at first glance, this might seem like a disadvantage, right? Because with a B tree, it's possible that I don't have to traverse all the way to a leaf to find what I'm looking for. I could find what I'm looking for halfway down the tree, or if I'm really lucky, I might find the data that I'm looking for right in the roots. It's entirely possible that it could be there. In this structure, we're saying the data only lives in the leaves. The internal nodes are only used for searching purposes, so I'm not going to store any actual data in the internal nodes. So that might sound like it's worse, because I'm going to always have to traverse to the very bottom of the tree to find a leaf node in order to get the actual data that I'm looking for. And actually that is slightly less efficient, right? But there's a much bigger advantage that we gain from doing things this way that's going to outweigh that slight inefficiency. Does anybody know what that advantage might be, how this helps us by having two different node types? It's a really important concept. So trees, how do they save us time in the first place over just a regular table? Where does the time come from? Where does the efficiency come from when I construct a tree to search for data versus just using, the heap file directly? How does that help speed things up? Talked about this on Wednesday, for sure. Yeah. I remove a big chunk of the tree every time I traverse from one node to the next, right? I reduce my search space very significantly. And so the more I can reduce my search space, the faster search is going to be overall. And actually, that's what this advantage is about as well, right? If I have a case where I'm storing data inside the same nodes as the tree pointers, right? That data is keeping me from storing more tree pointers. And the more tree pointers I can fit in a node, the faster I'm going to be able to reduce that search space. Does that make sense? Does it make sense why that's true? Right? I'm trying to reduce my search space as fast as I possibly can. So the more possible branches that I can have coming out of a node, the faster that search space is going to be reduced. So by eliminating the data from the nodes and having those the data only be in the leaf nodes, I am able to cram more tree pointers in the internal nodes than I could before, which will reduce the search space even faster than I was able to before. In other words, with a B tree, a traditional B tree, maybe it'd help if I drew a quick little diagram. With the traditional B tree, right, the search space reduction, whatever. Can I draw? Thank you. I've got data, and then I've got tree pointers in between, right? Data, tree pointers. So here, if I take one of these paths, I've reduced the search space by effectively 1/3, right? There's 3 possible paths I could take. If I didn't have this data here, it would allow me to fit more tree pointers in its place. So now I can replace these with additional tree pointers, and now by taking a path, I've reduced the search space down to 1/5 instead of 1/3 each time. That is the point that I'm trying to make here. That is the advantage that I'm trying to claim B+ trees have over traditional B trees. Are we good on that? It's a very, very important concept to understand before we proceed any farther. Does anybody have any questions about that piece? So what that means for us then is that we can now talk about the various properties that I expect these nodes to have, as well as how to construct these trees and work with these trees. Because, spoiler alert, next homework assignment, I'm going to ask you to implement one of these guys. That's the whole point of the next homework assignment. So we're going to talk about some algorithms for searching, insertion, and deletion on these trees. And before we proceed any farther, should introduce some terms. K is going to be the values that we are inserting or searching for or deleting. And then B is what's called the fan out. And we've actually been talking about the fan out this whole time. I haven't been calling it that, but that's what we've been talking about this whole time. What dictates the fan out? Do we get to choose what the fan out is? What parameters in my database are going to determine what the fan out of a tree is? Or if I go back and look at my diagram real quick that I just drew, we can talk about this a little bit more, right? I've got all these pointers. What are these pointers being stored in? Or where's the data of my index being stored in? What structure is it ultimately being stored in? A page, a heap page, right? Heap page. So what dictates how many pointers I can fit into a single node? Size of my heap page, right? Size of my heap page. So the heap page size is determining the fan out, which is ultimately determining the overall performance of the B+ tree, which leads to some interesting kinds of questions, right? We talked about this a little bit on Wednesday. Why not just crank the heap page size up to max? We talked about why that might not be a bad idea. Or I'm sorry, why that might be a bad idea, right? And so these are things worth considering, but I think the more important point, at least for right now, is to understand that one node is going to be stored on a heap page, and thus the heap page size determines the efficiency of this data structure. All right, cool. So then some other things to know about B+ trees. The number of elements that can be in a node is dictated by the degree of a tree. Now, this is a common confusion point because there's actually 2 degrees that we need to talk about. There's the degree of the inner nodes, which are used for searching purposes, and then the degrees of the leaf nodes, which are used to store the actual data, the values that we are searching the tree for, right? And there's slight differences in interpretation on that degree, whether you're talking about the internal nodes or the leaf nodes. So for an internal node, the traditional way that a B+ tree is constructed says that an internal node must have at least degree over 2 children. Must have at least degree over 2 children. Or the ceiling of the degree over 2, to be more precise. So what that means is if I have an internal node and the degree is 3, right? It must have at least 2 children. If it has fewer than 2 children, that node needs to go away. That node should not be part of my tree any longer, In other words, that's an indication to us that we need to rebalance the tree. We need to rebalance that tree. The one exception to this rule is the root. The root does not have a limit on the lower bound of children that it can have, and you can think about why this might be the case. If I'm constructing a brand new tree from scratch, it's possible that the root will necessarily have fewer children because they just aren't enough nodes yet to satisfy this condition. But once we get past the second level, this condition can be applied to all nodes on the tree. And so the way that this is constructed now is instead of having data in between those tree pointers, I'm going to have search keys in between those pointers instead. And so what our internal nodes might actually look like is something like this. Let me bring up my sketch again, see if I can sketch a more accurate B plus tree here. Here's an internal node, and I might have 3 and 7. These are search keys. They're not index values. They're not key value pairs. They're used only for searching purposes. And so then I might have some more child nodes down here, right? With other values in them. And if this is the bottom level of my tree, these would be leaf nodes. We haven't talked about leaf nodes yet, but if these, if there's more nodes below here, those would be further internal nodes. And so we can see now that I have a degree of 3 for this particular internal node, which means I can have at most 3 children. So in this case, P is equal to 3 for my inner nodes. I can have at most 3 children per inner node, but I must have at least 2. That also tells me how many search keys that I need for one of these nodes as well. I need 1 search key, right, for every child node, except for the last one. Because if I don't match any of the existing search keys, I'll just take the last remaining path. So the maximum number of search keys that can be in an internal node is degree minus 1. And I must have the ceiling of P over 2 minus 1 at a minimum. I know I'm throwing a lot of equations at you. We're going to do a lot of examples today that will hopefully drive these points home. The real thing that I want to illustrate right now is the fact that the degree of the internal node dictates how many search keys it can have, both the minimum and maximum, and also the number of children that it can have, both the minimum and the maximum. The leaf nodes are a little bit easier to understand than the inner nodes are. For the leaf nodes, remember the leaf nodes don't have any children. They're at the bottom of the tree. They contain key value pairs, right? So for the leaf nodes, the degree just dictates how many keys it can have, how many keys it contain. And it must be at least half full at all times. So I must have at least P over 2, ceiling of P over 2 keys at any given point in time. So if we look at this example, if we assume that these are leaf nodes with a degree of 2, they must all have at least 1 element in them, right? Although they might have more than that. That's okay too. So a degree of 2 for a leaf node indicates that it can have up to 2 keys stored in it, but has to have at least 1 in order to survive. And I want to point out too that while in class we're going to do a lot of examples with smaller degree values because it's just a lot easier to work with, in practice these degrees are huge, as big as we can make them. So in practice I would want to see degrees be in the hundreds or the thousands ideally, because again that's going to reduce my search space even faster. That's too much for us to do like on a chalkboard or on a whiteboard, so we're going to keep these numbers small. But in practice, I want to crank that up. All right, any questions about the structure of these nodes, how the degree affects what the contents of the nodes can be? Yes, question?
Where are the degrees of the internal nodes?
Yeah, why are they different? That's a great question. They could be different. It's entirely possible for them to be different. To understand why, consider the structure of the data that's contained within these nodes. So it's important to understand that every node is stored in a heap page, and so I always like to think, what's the what's the tuple that represents the data being stored in this node? So I have pointers and then search keys. That's all that's here, where the type of the search key is the same as the type of the column that is being indexed, right? Here I have sorry, my brain just shut off, right? I have key value pairs. Sorry, I have key value pairs. So I'm going to have key value pairs here where the key is the same as the column type being indexed, and the value is going to be a pointer into a heap table. So they're actually very similar in some cases, but you can see that the degree is necessarily going to be a little bit different just because of the definition of how that degree is used. In order to have the same number of search keys and index keys in a node, they have to be off by 1 just because of how the term degree is defined. In other words, these tuple sizes are roughly the same. I've got page pointers and then index keys in both nodes. So they theoretically can hold roughly the same amount of keys, right? But the way that the degree is defined for the internal nodes is based on the number of children. The way the degree is defined for the leaf nodes is based on the number of keys. So they're always going to be a little bit off from each other, but they can be close, like they are in this particular case. In practice, we want to make both of them as large as possible. So
once you get down to the leaf node, are you just doing
linear search? That's right, or binary search actually, because everything's stored in sorted order. Everything's stored in sorted order, and that will become very clear once we do some tree creation exercises here in just a little bit. Was there another question I saw over here? Yeah, what's up?
Why does the last node not have a search key?
So if I'm searching in this, and we'll do some examples of searching in just a moment, but if I'm searching here, right, the way that I interpret this is I look at the 3 and I say, all right, is the number I'm searching for less than or equal to 3? If so, I'm going to take this path. If it's not, then I'm going to look at the next search key. Is the number I'm searching for less than or equal to 7? If it is, then I'm going to take the middle path. And if it's not, I don't need another search key because there's only one path left for me to take. So I'm just going to take that one, right? I always am going to have, that's actually another very important property that maybe wasn't quite explicitly stated. The number of keys in an internal node is always going to be 1 less than the number of children that it has. Always, 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 always. Number of keys in an internal node is going to be 1 less than the number of children that it currently has. Yes?
So this is still reduction to 1/3, right?
I'm sorry?
It's no reduction to 1/3.
This is still a reduction to 1/3, yes, because I can have at most 3 children per node. That's right. Yep. And a lot of the examples that we're going to do are going to use small degrees like this. The algorithm, though, is written in such a way that it will work with any degree value. In fact, I'm going to expect your algorithms to be the same way, work for any degree that I might give to you. Any other questions before we move on? All right. So I believe the next thing we're going to do is take a look at some of the algorithms. There's three things in particular that we need to, 3 operations in particular that we need to talk about. Searching, so how do I find a value that I'm looking for? Insertion, how do I put a new value in the tree? And then deletion, how do I remove values from the tree? So we're going to start with the easiest one, which is searching. If I'm searching the tree, so I'm searching the tree for value k. This is actually a recursive search algorithm because it's a tree, and trees and recursion go together very nicely, like peas and carrots. So if the node is a leaf, I'm done because all of the data is in a leaf node. So I'm going to keep searching until I find a leaf node, right? So if the node is a leaf, I'm done. I've hit the bottom of the tree. I know the value that I need is in that node. So I just got to search the node for that value, and I'm done. If it's not a leaf node, If I'm in an inner node, then I have to decide which child I'm going to take next. And that's just going to be based on the keys that it contains. So you can see in this particular case that we're searching, this actually is searching the lowest search key. Am I less than the lowest search key? Am I larger than the largest search key? Then take either path on the end, because those are easy to check. If I'm somewhere in the middle, then I got to go through and look at the search keys in the middle until I find the search key that tells me which is the correct path to take. And then I'll just repeat that process over and over and over again until I found a leaf node, right? Until I found a leaf node. Or we can take a look at this in practice. If we wanted to try out an example of this. Oh, what did I do? Not what I intended. Okay, so if I wanted to search for the 6, for example, right? I want to find this 6 down here. I'm going to start at the root, and I'm going to look at the search key of the root and say, hey, is this 6 less than or equal to this search key? And my answer is, yeah, it is. So I'm going to take the path to the left, right? Then I'm going to look at these search keys. Is 6 less than or equal to this 1? No, it's not. So I'm going to check the next search key. Is this 6 less than or equal to this 6? Well, yeah, actually, it's equal to it. So I'm going to take the next path, right? And now I've hit a leaf node, and I'm done. I'm all done. So you could consider how that would work for other. It's very binary search tree-esque, right? Should not be any particular surprise there. It also works for cases so sometimes I'm going to search for a value that's not in the tree. That can happen, right? So if I'm searching for 10, for example, right? The 10 is bigger than 7, which tells me to go right. It's bigger than 9, which tells me to go right. And I get this leaf node that does not have a 10 in it, but I'll still check to see if it's there, right? And determine, the search just returns false in that case. It's not in the tree. Doesn't exist. The algorithm is still valid even if the actual key that I'm searching for is not present in the tree. And you notice that for this search to work effectively, I have to keep my tree balanced and I have to keep everything in sorted order. And so the insertion process and the deletion process, actually, for that matter, are what is responsible for maintaining this balanced tree and making sure that the keys, the search keys and the values of my leaf nodes are being inserted in the appropriate way so that searching can be efficient. And so those are going to be a bit more complicated. We kind of ate our dessert first. This is the nice thing. This is the wonderful thing about B+ trees. Very fast, very efficient searching. Now we're going to take a look at what we need to do to set that up. Any questions on searching before we look at insertion? Next. All right, so insertion is going to take a little bit more work, but this is kind of where the magic happens. Notice that for insertion, the first thing that it says to do is search. Search for the node where a new record should go. Everything is stored in sorted order, so if I'm making a new insertion, I want to make sure that it's being stored in sorted order. And the easiest way for me to do that is just to run a search to find where that value should go, right? Where should that value go? Once I have found that node, though, there's a couple of things that can happen. The easiest thing that can happen is that there's room in that node. If there's an empty spot in that node, that's the easiest possible situation. I'm done in that case. Just put it in one of the empty spots and move on with your day. We're done. I want to remind you that simple case is part of the reason why we're talking about these trees in the first place. Because when we talked about the single level indexing schemes on Wednesday, one of the biggest problems with them was the fact that they could not handle insertions and updates very efficiently. And so we now have the ability to be more efficient with our inserts and updates because there's going to periodically be empty spots in the tree. And we're actually about to see why those empty spots are there. So if the leaf node is not full, then we have work to do. I'm sorry, if the leaf node is full, I apologize. If the leaf node is full, then we have work to do. There's no more room in the leaf node, so I have to split it. I have to split that node into 2 new nodes. Half of the values are going to go in one node, the other half are going to go in the other node. And think about what that means for those new nodes. They're going to be roughly half empty, so that when future insertions come down, they have spots to go, right? There's empty space that's available for those new values to be inserted. I'm going to be very careful about how I split those values up too. Remember, everything has to be in sorted order, so I'm not just going to pick I'm not just going to pick half the values at random and put them in one node. I'm going to take the lowest half of the values and put them on one node, and the highest half of the values and put them in the other node, because they have to be in order. They have to be in order. Then, because I have an additional node, that means that one of my inner nodes is going to have an additional child. And because that additional child exists, I have to have an additional search key to go along with that child. So I'm going to take the largest key of the newest node and push it up the tree to the parent, so that the parent has a search key to locate the new node that we just created through this splitting process. Now there's a problem here. The parent, the inner node, might be full. Maybe the inner node already has the maximum number of children that it could possibly have. In which case, we're going to split the parent. We'll break it up into 2 nodes, and we'll repeat the process, right? Half the search keys go in one node, the other half go in the other node, and pass the search key up the tree. And we'll just keep doing this process until one of 2 things happens. Either we find an inner node that has an empty spot, it can accept a new search key, or we hit the root. Those are the 2 things that can happen. But this cascading process can either be very simple or can go all the way up to the top of the tree. If the root needs to split, then we're just going to create a brand new root. We've essentially added a new level on the top of our tree at that point. If I haven't found an empty spot in any of the inner nodes all the way up to the root, that means the levels are all full, and I have to add a new level to accommodate this new search key, this new node that I've created. So this is the pseudocode algorithm, which I think is going to be very helpful to you when talking about the homework assignment, but in terms of learning how this algorithm works, much better to go through an example. So let's go through an example. Here is an example of a search tree, and before we actually try to do the insertion, let's just talk real quick about the properties of this tree, right? The degree, actually, before we even get to the degrees, what kind of node is this? The top node? Inner node, right? Both of these guys then are leaf nodes. They're both leaf nodes, right? Okay, just want to make sure that that's clear before we go any farther. And then we can also talk about the degree. The degree of the inner nodes is what? It's 3. How can you tell? It looks like it can accept at most 2 search keys, right? Or it can have at most 3 children. It currently only has 2 children, but it looks like it can have at most 3 children. So the degree of these internal nodes is 3. And for a lot of the examples that we work with, that's going to be the number, that's going to be the degree that we use. The degree for the leaf nodes then is 2, because they can hold 2 values. They can hold 2 key value pairs, tops, right? So that's just to kind of set the stage. Now let's talk about inserting the value of 3 into this tree. The first thing that it says to do is to perform a search. Search this tree, find out where the value of 3 should go. So I'm going to start at the root, and I'm going to ask myself, all right, is 3 less than or equal to 5? Yes, it is. So I'm going to take the child to the left, and then I've hit a leaf node. It's right here. I've hit this leaf node. So this is the node where I want to put the value of 3. But there's a problem. This node is full. This node cannot accept any more values. So I have to create 2 nodes. Right? And half of the values are going to go in this node on the left, and the other half are going to go in this node on the right. But you might be asking yourself, well, wait a second, what's half? Because how many values do I have? I've got 3, 1, 3, and 5 that I need to figure out where they're going to go. 1, 3, and 5. So when deciding how to divvy these up, we really have two options. I can either put the 1 and the 3 on the left and the 5 on the right, or I can put the 1 on the left and the 3 and the 5 on the right. Correct? I want to make it clear right now that actually neither of those answers is wrong. There's many different ways to implement B plus trees, and lots of different points where you can, change things slightly and it's not going to have an effect. But what is important is that you are consistent. You have to be consistent. If I'm splitting nodes and I've decided that I'm always going to put the extra value on the left, then I need to do that every single time I split a node. I cannot decide to just randomly put the extra value on the right sometimes, and sometimes on the left. I either have to decide to put the extra value always on the left or always on the right. And for the sake of this class, just to keep us all on the same page, I'm going to choose the left. If I ever have a choice between left and right, even though it might not be necessarily wrong to go to the right, I'm going to choose the left, and I'm just consistently going to choose the left. So I'm going to say 1 and 3 go over here. My extra value is going to go on the left, and the 5 is going to go here. Does that make sense to everybody? We're not done, though. We're not finished yet. Not finished yet. Because the last part of the algorithm has to do with the search keys. Notice that right now, I've got 3 children of my roots, the 2 nodes that I drew out, and then this guy who's still just sitting up here, right? But I only have 1 search key in the root, so I need to pass a search key up the tree. So the algorithm says, look at the largest value in the new node that you created. Well, which one's the new one? That's a little bit ambiguous. Here's another way of thinking about it. I'm going to pass the middle value up. If I line all these up, 1, 3, 5, whatever's in the middle is what I'm going to pass up the tree. So in this case, I'm going to take the 3 and pass it up to the root. So that when this insertion is finished, I would expect to see a 3 and a 5 in the root. Another way that you can use to verify that this is being done properly, right? If I see a search key in a node, every single value that I find to the left subtree of that search key should be less than or equal to that search key. If that's not true, then something got screwed up along the way. So when this is finished, I think I actually have this drawn up on the next slide here. When this is finished, right? I've inserted the 3, it's split it off. The 1 and the 3 go to the left, the 5 goes to the right. I've taken this 3 and I pass it up the tree. And so now the root has a 3 and a 5 in it. Here's the result of our insertion. Everybody with me on that one so far? Let's try a few more. So now we're going to insert a 12. Same process. First thing I need to do is figure out which node it's going to go into. And for small examples like this, it's probably obvious, right? But for larger examples, I think it is definitely worthwhile to go through the search process, understand how the search process works. In this case, we know that it's going to go on this node down here on the right. It's going to go in this node right here. But we have the same problem that we had before. This node is full. Okay, well, we just talked about what to do with that, right? We just talked about how to solve that problem. I need to split this into 2 nodes. And then we said, since I have an extra value, that's going to go to the left. So 7, 8 goes here, and then 12 goes here. What's the next step? I'm not done yet. What's the next step? Search key. Pass a search key up the tree. So what search key am I pushing up the tree? 8. I'm pushing the 8 up the tree. That's right. But we have another problem, right? This 8 goes up to the root, but the root doesn't have any room for it. The root is full. The root is at its maximum capacity. So we're going to split the root. we're now going to split the root. 3, 5, and 8 are the numbers that we have. So I'm going to create 2 more. These are now inner nodes that I'm creating, not leaf nodes, right? Because I'm talking about search keys. I'm going to have 3 and 5, and then 8 on the other. And I'm still not done. What do I have to do next? I have to pass 5 up. And this is another confusing part of the algorithm. I'm going to be right up front with you. This is another part of the algorithm that people struggle with. When I pass a value up and I'm talking about the leaf nodes, I'm actually passing a copy of that value up the tree. So I'm going to see the 8 appear in a leaf node. I'm also going to see 8 appear in one of the inner nodes. When I'm splitting an inner node and passing a search key up, I'm not passing a copy up. I'm actually taking this 5 out of this node, right, and passing it up the tree. Does that make sense? It's slightly different how that works for leaf nodes versus inner nodes. Another way of thinking about it is this. I should only see a search key appear in my tree once. If I see a search key appearing in my tree more than one time, that's a clue that I've messed up part of this process. I might see a value duplicated in a leaf and an inner node. That is okay. But if I see the same value appear in more than one inner node, that is a problem. So I'm going to pass this 5 up the tree, and what I actually end up with is a 5 in my root. The 3 and the 8 nodes now become children of my root node. And then this diagram is getting very messy, but I would have children looking like this, which is probably going to look a lot nicer if I just stop sketching and show you the completed result. Here's what this tree would look like after splitting off, after inserting a 12. That was a lot of work just to put the 12 in. We hit one of the very most extreme edge cases, which is splitting the root, right? Splitting the root. It can happen, and it will happen. If my tree is going to grow, that's going to happen, right? It's just part of the growth of the tree. Are there any questions about that? We're going to do more examples of these, by the way. Let's do an easier one. Now I want to insert a 9. I want to insert a 9, so I'm going to do my search. 9 is greater than 5, so I go to the right. Oops, sorry. 9 is greater than 5, so I go to the right. 9 is greater than 8, so I go to the right. I end up in this node with the 12, and oh, there's an empty spot. That's the easy case, right? Empty spot, cool. Put the 9 in, I'm done. No search keys to update, no splitting to worry about. We're done. That's it. So here's what the tree looks like. All right, I want to insert a 6, right? 6 is greater than 5, so I go to the right. 6 is less than 8, so I'm going to go to the leftmost node, which is going to take me to this node here with the 7 and the 8. But the reason why I have this included on the list, why I like to talk about this, is because a lot of people say, well, wait a second, right? Why didn't you just put the 6 next to the 5? There's a spot there. 6 is greater than 5. It seems like that should work, right? Why did you send the 6 to this node that's full when I've got a spot for the 6 sitting right there that could work? We have to do this algorithmically. We have to do it the same way every single time. That means following the search process the same way every single time. The search process says, right, use the search keys to tell me where this value should go. We as humans might look at this tree and say, hey, that doesn't make sense. Put it here. But the computer is just following the instructions that you've written, and those instructions are going to be consistent every single time. We must view things from the computer's perspective, the computer's point of view. So the 6 is going to go in this node with the 7 and the 8. What's going to happen next? We're going to split that node up, and then which search key is going to get passed up? 7. So then the internal node with an 8 is going to now have a 7 and an 8, right? Oh, I guess I don't have that diagram on here. Sorry. A 7 and an 8. Are there any questions about that? process. Any questions? We're going to get some more practice, but before we can do practice problems, we have to talk about the final operation, which is deletion. So let's do some deletion examples, and then I'm going to turn you loose on some B+ trees. All right. Hopefully it should come as no surprise that the first step of deletion is to search for the node where that record should be. And then we're going to look at the easy case. If I can remove that value from the leaf node and it's still more than half full, it still meets the criteria based on the degree, then just delete it and we're done. Easy. If I delete that node and it's less than half full, it doesn't meet the degree criteria, then I have to get rid of that node. And this is where things get complicated. So if I'm going to get rid of the node, there's a few things that I can try to do. The first thing that I'm going to try to do is steal a value from one of my siblings. You may have noticed that on these diagrams, on the leaf nodes, I've actually got them set up like a linked list. And the purpose of that is so that if I need to, I can go to my neighbors, right? I can go to my siblings and try to steal values from them. If my sibling has an extra value, then I'll just steal one from them. That's the easiest solution to me being less than half full. If I look at my siblings and I try to steal a value and they don't have any value, so they're also very close, right, to the cutoff for staying alive, then I'm going to merge. I have to merge with one of my siblings. So I'm going to combine all of our values together into one leaf node. And now my parent is going to have an extra search key, right? My parent is going to have one search key too many. So I have to delete the search key from one of those values, from one of those nodes out of the parent. But notice that we have the same problem that we had with insertion. If I delete that search key and my parent is less than half full, my parent no longer has enough to survive, then I'm going to repeat that process again. But the process with internal nodes is actually very different than leaf nodes. I cannot, if I'm an internal node, I cannot simply look at my siblings and try to steal a value from them. That is not possible. Consider why that's the case, right? Because the tree has to remain balanced, and the search keys are stored in a particular way that prevents me from being able to borrow from siblings. So instead what has to happen, this is something that will be much easier to show you with an example than talking about it, is this push-through process where I'm going to go actually to my parent and say, hey, can I have an extra value? The parent will go to my siblings on my behalf and say, hey, can I have an extra value? And then those values will be pushed through the nodes. I have an example that I'll show you actually of that in just a little bit. So let's do some walkthroughs. Let's see if we can explore the various paths of this algorithm for deletion. So the first thing that it wants us to do is delete the 5. So if I look at this, tree, first thing I do is I search and I find the 5. All right, here it is. I found it. What's going to happen next? I'm going to take the 5 out, and then what happens? We're good. We're good. The leaf node has a degree of 2. That means it has to have at least one value in it. If I take the 5 out, it's still okay. This is the simplest case. If the node is very full, this will happen. This is the easiest possible case. I'll just take the value out, and we're good. Nothing else to do. Okay? All right, now I want to delete the 12. All right. First thing I'm going to do is find the node where the 12 lives. It's right down here. I'm going to take the 12 out. And now I've got more work to do. I take the 12 out. This node is now less than half full. It's empty, right? I want to make it very clear, though, that the next step is not to simply remove the empty node. The next step is to merge. Actually, no, I'm sorry. I skipped a step. Did anybody catch the mistake that I just made? The next step is not to merge. What's the first thing I'm going to try to do? I'm going to try to borrow from a sibling. I'm going to try to stay alive by stealing from my siblings. It's a very true to life thing, right? It is. Don't tell my sister I said that. Actually, you can. She knows it's true. So I'm going to go next door and say, hey, do you have an extra value? And do I have an extra value? Yeah, in this case, I do. I do have an extra value. I can do that. So I'm going to take one. Which one am I going to take? Definitely the 9, right? Because I have to keep things in order. Have to keep things maintained in order. So the 9 is now going to go over to this node. The node's going to live. The node's going to survive another round. Okay? So we're going to borrow. All right. Now I'm going to delete the 9. Now things will get a little bit more interesting for us. So if I delete this 9, now this node is empty. First thing I'm going to do actually is try to borrow, right? I'm going to go to my sibling. I'm going to say, hey, you got anything? And this time sibling's going to be like, nope. I've got 1 value. I need that. If I give it to you, then I'm a goner. So I'm going to keep it. And so now, even though it might look like what we're about to do is remove this node entirely, the true way to discuss this is to merge. We're merging these 2 nodes together. It's very important. Consider, in this particular case, the degree is so small that it looks like we're simply removing a node. But if the degree was much larger, right, I would trigger this process while there were still values here. So it's a true merge. It's not simply removing an empty node. I'm merging these 2 nodes together. So I now have a new node with just an 8. And that's it. Do you see the problem, though, with this particular situation? If I look at the parent node, I no longer need this search key. Or in other words, this parent only has 1 child. So now the parent is below the minimum. The parent needs to have at least 2 children to survive, and it currently only has 1. Currently only has 1. So this is now a problem. And what the parent is going to do, it's actually not going to go directly to its sibling. It's first going to go up to the root and say, hey, I don't have enough to keep going here. Do you have any extra values that you can give to me to keep me alive, right? To maintain my minimum. And the root's going to say, well, hang on a second. Let me go ask your siblings for you. So the root's going to go down to its sibling and say, hey, do you have any extra search keys that you could give me so that I can distribute this over to your sibling, right? And actually, this node does. This node can afford to give up a search key. And it will. Which search key is it going to pass over? Kind of. In order for this tree to maintain the correct search keys, the 6 is going to go up to the root, and it's going to push the 7 out of the root. That's why we call it a push through, right? I can't just pass the 6 over here. That would not work. The search keys would be in the improper order. Do you see that? That would not work. Instead, we have to push it through. The 6 goes up to the root. That pushes the root search key out the other side down to the sibling. So this sibling actually, this diagram is kind of messy, I know. This sibling actually ends up with a 7 over here. The 6 ends up in the root. And then this sibling is left with just the 1. And we're still not quite finished yet, right? We're still not quite finished yet because I have to make sure that all of my child pointers now conform to this new view of the world, right? If the 7 is here, the whole reason I did that is so that this inner node could have more than 1 child. So it's now not just taking the 7 search key, but it's also taking that child as well. It's not just taking the search key, it's taking that child. So now it's got these 2 nodes as children, the 7 and the 8. Let me show you a clean example of this that I haven't, oh, well, I guess I don't have one, sorry. I could redraw the whole thing if that would help. The root will have the 6. Oh, wow. It made a nice rectangle for me. Thank you, computer. 7. Oh, goodness. I knew it was coming, and it still surprised me. Is it going to do that one? Oh, man. This made my day. Oh, it didn't do that one. Okay. What was the other key? It was a 1. I don't remember what other child nodes were over here. What were these child nodes down here? 1 and 6. Didn't like that box. Okay. So this is what it will look like. This is what that tree will look like after that push-through effect has happened. Is that clear? That's the most complicated case. That is by far the most complicated case. Although, there's perhaps even another case that's worth discussing that is not on this particular example. What if I delete one more value? What happens then? So now let's delete, I don't know, it doesn't actually matter which one I delete, right, at this point in time. If I delete one more value out of this tree, any value at all, what needs to happen? I'm collapsing this tree down a level now, right? I'm collapsing this tree down an entire level. If I take one more value out of here, that means I've got 3 leaf nodes total, and I don't have enough leaf nodes to support this number of inner nodes. I don't have enough. I don't have enough. So this entire second level is going to collapse. And what I'm left with is a root with a 1 and a 6 that points to these 3 remaining leaf nodes down at the bottom. Do you see that? The algorithm actually accommodates for that, though. The algorithm actually accommodates for that. The algorithm would say, all right, you deleted the 8, right? Try to do the push through. I can't because there's nothing for me to push through anymore. There's nothing for me to push through anymore. So at that point in time, we have to merge the nodes with the parent node, basically collecting all of the keys on a higher level in order for this to succeed. Are there any questions about that? Yes?
So when we deleted, this happens on this one actually, but when we deleted 12 from the tree, the search key in the right inner node updated from 12 to 9 or 9 to 8, I don't remember.
Okay.
Can we look at that again?
Yeah.
Yeah, so how is that update happening? Are we deleting that key and then like re-adding it, or?
How is this update happening? So it actually was 9 and then switched to 8. So I assume that's what you're referring to, right? We deleted the 9 out of the, actually we deleted the 12 out of the tree, right?
Yeah.
And so the effect that had was we borrowed the 9, and this search key, I should have mentioned this when we did the borrowing, and I just overlooked it. I'm sorry about that. I borrowed the 9, and now this search key is now invalid. Do you see how that's the case? The 9 is not sufficiently pointing in the right direction. So because I stole the 9 from a sibling, it required me to update the search key to keep it valid. You can think of that rule I mentioned earlier. The search key is indicating the largest value that appears in the leftmost subtree.
Right. Since this borrowing is happening at the level we directed from, how does the parent, like how are we
the child would have to notify it. So the way I would expect that to happen in this case is the child with the 8 and the 9, once that 9 was stolen from it, that child now knows that the search key pointing to it may not be valid anymore, because anytime the largest value gets removed from a node, that could mean that the search key is no longer valid. So that child would then notify its parent, hey, my new largest value is 8. Do whatever you need to do with that information. Yeah. I think that's an important point. I think the child definitely does want pointers back up to the parent. That's true even for the stuff we were talking about with insertion, right? You know, when we split the new node and pass the search key up the tree, we have to have pointers from the child up to the parent. I also think these diagrams are a little bit insufficient. Even when looking at this linked list down on the leaf nodes, it seems as though it's singly linked going one direction. I think doubly linked is certainly appropriate, especially when you consider the case of borrowing. I want to be able to borrow from either side if possible. So I think a doubly linked list here is a better way to go. I do also, I mean, while we're on the topic, and maybe I'll touch on this a little bit more when homework 3 rolls around, it's certainly possible to get away without this linked list on your leaf nodes, but so much easier with it. I see people try to do the assignment without linking their leaf nodes. So much easier with that linked list on your leaf nodes. Please, please, please do it. Yes?
So, so when the child notify the parent that the largest value has been removed, we have to update. So do the parent have to go to the other sibling and ask for the lowest value, or can the parent just be updated?
Well,
the value larger
so when the parent is notified, I would expect it to be notified, and also that notification will include, here's my new largest value, right? And also, you know, it's possible, like, too, that maybe the parent doesn't actually have the search key. Maybe the parent of the parent has the search key that's been affected. Like if this 7 were changed for whatever reason, then it's actually not the direct parent that has the 7, it's the parent of the parent. So even if the parent doesn't have any work to do as a result of the search key being updated, it still needs to notify its parent. In fact, anytime I'm changing search keys through deletion, I really need to follow those search keys all the way up to the root just to make sure that I've if I found the search key, I can stop because I know the search key is not going to appear more than once. But if I haven't found the search key, I need to keep traversing until I hit the root, potentially.
Yeah, so can the search key in the parent be updated to like 8.5 if allow?
Well, the type of the search key is going to be the same as the type of the key. So it's going to be, if I'm indexing a column with an int, it's going to be an int. So we don't need to play little tricks like that to make it work, right? I can actually update it to the proper value. In this case, since the 9 is no longer valid, I'll just update it to the proper value, which is 8, right? This child node is going to notify its parent, hey, somebody took my 9, my new largest value is 8, and then the parent will say, oh, I had a 9, but since you told me it's now 8, I'll just switch it, and then it's good. Yep. Yeah, in the back. The last insertion example? Sure.
So after we add the 6 with 7 and 8, but when you update the node as well, we have pointer to the 9 as well.
So the question is, I insert the, let me make this drawable. The question is, we insert the 6. We insert the 6 here, right? Which actually means making 2 nodes. I did that wrong. 6 and 7, and then there'd be 1 node with an 8, right? So what search key is getting passed up the tree in this case? 7. So I pass the 7 up here, and there's a spot for it. So this node will now say 7, 8. And in terms of the children, these search keys are still effective, right? This is the leftmost child, this is the middle child, and this is still going to be the rightmost child. And these search keys are good enough to search for all 3 of those pathways. Is there another question? Yeah.
You put the slide with
Delete 9, sure. Okay. The one before, okay.
Yeah, so in this case, if you wanted to delete the 7, would you merge the children or would you borrow it?
If I wanted to delete the 7, oh, good question. Yeah, great question. If I wanted to delete the 7, so something that I didn't touch on because it didn't come up when I was going through the exercise, when it says to borrow, it actually says if sibling with the same parent is more than half full. Yeah. I'm glad you brought that up though, because it is an important piece of the algorithm. So I would try to borrow from the 6. I would actually not try to borrow from the right-hand side. If I was in the middle and I actually could borrow from either the left or the right-hand side, this is another situation where it's not necessarily wrong to take from either side, but we need to be consistent. And I'm always going to favor the left. I'm always going to try going left first and then go right. And I'm going to keep repeating that because I think it's important for us to all be on the same page. B, I also want you to be aware that if you look at other B+ tree implementations, because it's a very common data structure, people sometimes find little B+ tree demos online that favor the right-hand side. Those are not wrong. They're just slightly different implementations than ours. So please be aware of the fact that we are making a conscious choice here to favor the left side. Favoring the right's not wrong. It's just a different implementation decision. We have about 15 minutes left, and so what I would like to do, and we'll actually spend some time doing this probably on Wednesday as well, because these are just really good examples to go through to get you ready to work with these trees. Using a B tree, that should say B+ tree. I don't know where the plus went, sorry. A B+ tree with the degrees shown. Run through the insertion of these values in the order that is given. So I'm going to give you 5 or 10 minutes or so, and then we'll sketch this up to wrap up the day in just a little bit. Let me know if you have any questions. I'll be around.
It was like so. Well, we had a different. Maybe the rules change.
All right, I understand some of you might still be working on this. We are running a little bit short on time, so I'm going to go ahead and get started on it, and hopefully we'll clear up any issues you ran into along the way. We're starting with nothing, starting with a blank slate, right? First thing I want to do is I want to insert a 9. So that might seem easy enough. I'm just going to have a single node with a 9 in it, right? What kind of node is that? This is my entire tree. What kind of node is that? It's a leaf node. It's a leaf node. This is a special case, right? When I first create the tree, if I only have a single node, it is a leaf node because it contains values, contains the data. That is not a search key. That is the actual value. That is a leaf node. That is a leaf node, and so it must follow the leaf node rules, right? So when I go to insert a 4, that's not terribly complicated, right? I now have a 4 and a 9, and this is still a leaf node. That fact has not changed. Okay? When I insert a 12, that's when things start to get a little bit more interesting. So I'm going to insert a 12, and I don't have room for it. So what is this? What does the algorithm tell me to do? I gotta split. So I'm going to have one node. Oh, that's a square. Okay. I'm going to have one node. I'm sorry, I'm going to have 2 nodes now, sorry. What's going to go in the left node? I have 3 values, 4, 9, and 12. So what goes in the left node? 4 and 9 and the 12. Remember, I'm always going to favor the left. If I have an extra value, I'm going to put it on the left. Always going to favor the left. All right, then what? Are we done? I have to pass the search key up. So what's the search key? 9. So I'm going to pass the 9 up the tree. There is no node there. So we're going to make one. We're going to make a new root node. And now this is an inner node. For my root, it contains a 9. And here's how that hooks up. So after inserting the first 3 values, here's what we got. Those first few values can be a little tricky because we're starting off with a leaf node and introducing more inner nodes. It can be a little bit tricky. Any questions on that? All right, so then we're going to insert a 7. So I'm going to try to insert a 7 into which node? The left or the right? The left. The search says go left and try to insert the 7 in between the 4 and the 9. So I have another split, right? I have another split. So, okay. What goes on this leftmost node? What? Okay, 4 and 7, which means the 9 must be over here, correct? And then what happens? I pass the 7 up the tree. The middle of those 3 values gets passed up the tree. This 9 that's sitting here is still a valid search key, right? That's still okay. The 7 is also a valid search key, and then I just need to update my child pointers a little bit to point to the proper nodes, like so. So here's what it looks like after inserting the first 4 values. Everybody with me so far? Any questions? All right, so we've done the first 4. The next thing to insert, no, I didn't want it. The next thing to insert is a 2. So I want to insert this 2. Where's it going to try to put it? It's going to try to put it over here. There's no room. There's no room. And this is where some people would say to me, well, all right, just kick the 7 out and put it over at in the node with the 9, right? There's room. Just kick the 7 out. Is that what the algorithm says to do? No. Algorithm says if the node is full, split it. Split it up. So I'm going to have a new node, and the 2 and the 4 are going to go here, and the 7 is going to go here, right? I'm going to do what we've been doing. I'm going to pass the search key up, which is the 4. But wait a second. I try to put the 4 up here, and this node can't accommodate it anymore. Remember, the degree of my inner nodes is 3. Actually, I should have just, yeah, it's right there. It's a 3, which means what? 3 refers to what? The number of children that it can have, the maximum number of children that it can have. I'm already at the maximum. If I insert a new search key, that means I'm trying to append another child node. I cannot have 4 child nodes. I can only have a maximum of 3. Degree of 3 means 3 children at the most. So what does that tell me to do? Split. I'm splitting the inner node now. I'm splitting the inner node. So 2, 4, 7, 9, 12. I need to redraw this diagram. 2, 4, 7, 9, 12. Whoa, where did that come from? Oh. Okay, sorry. So I had a 7 and a 9 up here, right? And now I'm adding a 4. What's actually going to happen? What are my inner nodes going to look like on this level? Or maybe a different way of phrasing it is, which value is going to get passed up? The 7. But when I pass up values from the inner node, I'm not making a copy of it. I'm actually literally taking this 7 out and passing it up, right? So I'm going to have these inner nodes that say 4 and 9, and then another new level up here that contains the 7, and then just connect all these child pointers up as best as I can. A little sloppy, sorry. And so after inserting the 2, right, this is what we end up with. We are officially out of time, so I'll tell you what. This is important, so I will keep this beautiful sketch and we'll continue it as a little review on Wednesday, and then we'll actually do a deletion example on Wednesday as well. Have a good week, everybody. I'll see you in a couple days.